Okay guys, so today we are going to be looking at about slides 3 through 19 of your Sedimentary Rocks PowerPoint. So I'm just talking to you today about some of my favorite things, some of what I think are some of the most exciting things about sedimentary rocks. So we're just going to kind of go through. I've got a whole bunch of different rock samples, so we'll get in really close and see some nice stuff going on. So get a good idea of what kind of things happen to create sedimentary rocks, which make up about 90-something, much higher, I think, 90-something% of the rocks in Kentucky, and about 70% of the rocks in Kentucky are limestone. So we'll be talking about limestone a bit, though there is a lab later on in the semester, Lab 11, I believe, that focuses more on our local fossils and rocks. So today we're kind of focusing on all sorts of different kinds of sedimentary rocks, but the processes that create them in the first place. You can go through the rest of the PowerPoint, learn how to identify, tell the difference between a conglomerate and a sandstone and all those sort of things, but we'll kind of focus on how sediment's created in the first place. So we're starting out slide 3 through 7 or so with it starts out with physical weathering. I don't really have a lot of cool examples of mechanical or physical weathering here. We have a lot of things that can happen. Exfoliation is one where granite or some other type of rock that forms under quite a bit of pressure and heat deep inside the earth, metamorphic rocks especially, once they're exposed, they begin to kind of flake off. They're getting exposed to less pressure than they were before, so that's something called exfoliation or onion skin peeling, where they kind of start to kind of break apart. We see that a lot with Yosemite and the Half Dome. So that's pretty cool. Tree roots can get in between rocks and kind of break them apart. You've probably seen that happening to retaining walls here in the Cincinnati area. Happens to rocks in nature too. Yeah, so mechanical weathering processes are kind of cool. I want to go ahead and start and dig into some things that sound a little more complicated, and they are, I guess, but they're also more interesting to me, and they are things that you're probably kind of familiar with too in your day-to-day life, especially if you eat a lot of Mexican food, right? Yeah. But anyway, we're starting out with looking at chemical weathering processes. And the first one here, I'm going to do a little example with you. This is looking at something called dissolution, or the ability of a material to dissolve. Not many rocks can dissolve. You can probably imagine rocks are pretty solid, they're pretty hard, they're pretty durable. And that's kind of true for a lot of rocks and a lot of minerals, but not for everything. There are plenty of minerals that once exposed to water, especially if it's acidic water or hotter water or than colder water, things like that, they can actually dissolve. Not too different than putting a lot of salt into a pot of water that you're going to put pasta in later. That salt does what? It kind of disappears. It doesn't disappear, you can't see it anymore, but the water pulls apart those sodium and chlorine atoms, and that's dissolution. That's going to happen here with my antacid tablets and my fake Alka-Seltzer, and we have just some plain tap water here. So this is really just, and you can look at the back of okay, there's aspirin, all right, we're not going to see that in nature. Sodium bicarbonate, that is basically limestone, or part of limestone. So we have a lot of calcium in here, we have bicarbonate, and that's a big part of what makes up limestone and a lot of the carbonate minerals, right? So going back to our minerals, the carbonates like calcite, aragonite, things like that, dolomite perhaps, to an extent. So this is made out of the same kind of thing, and that's actually something that limestone is mined for, is for medications. So I'm just going to drop this in here, and we're seeing it fizz pretty rapidly because sodium bicarbonate is actually more like baking soda, and baking soda reacts with acids in your baking products. Like the reason why they have baking soda, baking powder, salt added to things like your cake mix is because it produces a gas, just like this is doing, and that helps your baked goods to rise with the absence of yeast. If you're not using yeast, you need to use a chemical leavener, and this wasn't invented until like the mid-1800s, a chemical leavener to get your baked goods to rise. So that's exactly what is happening here. Why do we care? It's because we're in Kentucky, and this is how caves are formed, because much of the surface of Kentucky is covered by limestone, which reacts with water. slightly acidic rainwater. And as we get into groundwater and caves later, we'll be digging into that further. But we're looking at how limestone is being dissolved very slowly by rainwater, raining down on it, kind of eating away at the limestone, dissolving bits and pieces of it, and carrying it away in solution. Later on, in a cave system, it could drip from the ceiling once it's saturated with that limestone solution, and leave behind a very cool rock formation called stalactites, stalagmites, columns, flowstone like cave bacon, all sorts of cool things like that. So we have processes of dissolution, but then recrystallization or redeposition of a chemical sediment happening in a cave. And that's happening in Mammoth Cave. You can take the frozen Niagara tour of Mammoth Cave and see a lot of that flowstone and see a lot of what's happening with water dissolution. So you could say that it looks like the Alka-Seltzer has disappeared, and of course it hasn't. The water molecules have pulled apart the sodium, the carbonate, some other, not a whole lot else in here, and in that process, it's completely dissolved it. So now this water, I'm not going to drink it because I feel okay right now, but this water has gone from close to neutral, because it's just tap water, to being pretty basic. And that's something that you would drink while it's still fizzing. Right now, though, it has gone back to neutral because that interaction is done. It's no longer fizzing. You know that we could do that because back when we were testing minerals, we were able to test one mineral in the lab for sure. We knew exactly what it was by dropping a little bit of hydrochloric acid on it. Sorry, I'm just kind of running around here. So I have a sample of a rock that contains a lot of calcite. This is a local limestone from along the AA highway here in northern Kentucky, and we drop some acid on it. You guys know what happens. We'll do this more with our sedimentary rock lab, but it fizzes, and that's how we identify calcite. It's also how we identify all the different kinds of limestone, whether it's travertine, fossiliferous limestone like this, oolitic limestone, micrite, chalk, a whole lot of different kinds of limestone, and the acid test is very helpful. So we are actually causing a little bit of dissolution to happen. Okay, we'll go back to that guy in a little bit. So that's a really cool type of chemical weathering that's very special to us here in Kentucky because it allows us, it creates caves first by causing big open passageways, but then also creates cool cave formations by redepositing that sediment by dripping from cave ceilings. All right, so we have some other, and again, these other two kinds of chemical weathering, well, this one especially is one that we're kind of familiar with. This is a piece of basalt, which is a rock that forms, we did igneous rocks already. You're pretty familiar with basalt. It's what makes up most of the oceanic crust. It's what forms from lava flows out of volcanoes in Hawaii. It's a very common igneous rock. But you also know that it's containing ferromagnesian minerals, right? Like augite, maybe some hornblende, some olivine, and those ferromagnesian minerals contain iron. Okay, yeah, so they contain iron. Well, iron, once it gets rained on, as you know, if you've ever left a bike out in the rain, it rusts. So we have a rock here that's been broken, and it didn't look like anything, just kind of a rusty, red. There's lots of reddish brown rocks, nothing very special. But we break into it, and it is basalt, where the outside of it has been rusting. This happens relatively quickly, and is the reason why there's not a lot of black sand beaches, because basalt doesn't physically break down to the point where it creates a lot of sand. It is going to rust. It's going to weather away chemically, and then the iron oxide moves away with water and is deposited elsewhere, and often stains other rocks, which is why many sandstones that don't contain any of these iron-bearing minerals will be stained orange or red because the water has put iron oxide there. Red River Gorge geological area in eastern Kentucky is a great place to see rusty red sandstones. There's no ferromagnesian minerals. We just have the remnants of where those were weathered away a long, long, long time ago from the erosion of the Appalachians. Okay, moving on to the next form. So this is oxidation, right, or rusting. So we have dissolution, oxidation, and our third type of chemical weathering is something called hydrolysis. Hydro. That makes us think of water. So once again, we're dealing with water. Water does a lot of cool things, and in this case, we have a piece of granite I'm not sure where this is from, but one of the neat things that's happening to it is there's kind of blobs of quartz that are sticking out, because quartz isn't going to chemically weather away. Nothing happens to quartz. It's silicate and it's oxygen tied together very tightly, water, acids, nothing really tends to break that down. So quartz is going to be the most resistant mineral to weathering. What is happening though is granite also contains an awful lot of feldspar, and feldspar reacts with the process of hydrolysis to create a very special group of silicate minerals that we haven't talked about yet because they don't form from igneous processes, they form from weathering, the clays. So clays are actually a very diverse, very informative for geoscientists group of minerals, and they're very special because they form from the chemical weathering of feldspar, a few other different kinds of minerals too. But as feldspar makes up over 3/4 of all the minerals on the surface of the earth, you're going to get a lot of clay. And once clay forms, even though it's very fine, very soft, gets washed away very easily, it's not going to chemically erode any further. It is the product of chemical weathering, so it's done. So that's hydrolysis, and this is the process by which basically mountains break down into mud. So that's kind of the fate of all mountains. Even if they're made of this really hard, sturdy granite, they do get wet, and that feldspar that makes up the majority of granite will turn into clay minerals. Okay, so moving on, we're creating sediments. We have a couple different kinds of sediment. We are creating siliciclastic sediment, or you could just call that clastic, or you can call it detrital, whatever you like. I like to use the word siliciclastic because it's kind of fun to say, but also it reminds us that when we're looking at siliciclastic sediments, like sand, mud, from the silicate minerals like clay, right? Gravel, pebbles, all these little bits made from previously existing igneous or metamorphic rocks, we're looking at silicate minerals. So that's a good way to remind us that, hey, if we're identifying silicate minerals, it's probably a siliciclastic sedimentary rock. There are exceptions. Another type of sediment, though, and I'll talk about this again towards the end, is chemical or biochemical sediment. Now, I like to combine these into one group because chemical are formed from processes like evaporation, things like that, without the help of animals. Biochemical indicates that we're looking at the remnants of plants and animals, but really these guys have just taken chemicals out of water and have used it, and that creates a sediment. So either way, chemically it's kind of the same thing. So I like to group them together. So this is going to be a chemical type of sediment, first of all, that we're looking at, and this is just from a very salt-rich body of a little pool of water I had that I allowed to evaporate. So we have a crust of salt. Kind of weird, how do we find this in nature? We identified halite, or the mineral salt, back with the mineral lab, but where do we find like a crust of salt in nature? Think of a place where evaporation is very extensive and dominates the landscape. If we have water, like a shallow lake that's full of a lot of minerals in it, and that water evaporates, well, the minerals don't evaporate. They're left behind, and they form little crystals of salt or gypsum or barite. There's several evaporite minerals, but they're forming a sedimentary rock called the evaporite sedimentary rocks. And so rock salt is one of these. So a good, think about a city that has the word salt in it, right? Salt Lake City, Utah. A really good example of where there used to be a huge, extensive, what was called Lake Bonneville during the last ice age, has been drying up, and is continuing to dry up, and we're left behind with crusts of salt. So we're looking at desert habitats. So when we find ancient sedimentary rocks like sandstones or siltstones that have a layer of crystalline salt or gypsum in there, we know that there was a at least seasonal, if not permanent, dry time. We're looking at some very dry places, a lot of evaporation for that to occur. We know a great deal about the history of the Mediterranean Ocean because of the periodic, throughout some past major climate shifts, the periodic sea level rise and drop again of the Mediterranean Sea. So this can point to very shallow sea environments too. Usually we're looking at deserts though, because the entire ocean's drying up is not the most common thing. Okay, so we're looking at some different kinds of sediment, how they behave, how they change during weathering, and now erosion. So we kind of covered weathering here, we created some sediment. Erosion incorporates the idea of transportation. So now this sediment that we made is going to move. We're looking at gravity now. Didn't really focus on that too much with igneous rocks, but now with sedimentary rocks, we're thinking about how a mountain made up of something like a granite is now going to change. That sediment's going to break up physically, chemically go through changes. It's going to tumble down the mountain, end up in a stream somewhere, maybe windblown in the desert, continue to move and make its way all the way to as far as it can, which is the ocean and some of the deepest parts of the ocean. Some of that sediment will make up. Now, it's important to know, you're not getting chunks of granite in the deepest parts of the sea. It's being changed a lot. Hydrolysis, oxidation is going to happen to some of the minerals, perhaps in granite. These are going to occur, dissolution maybe, but we're going to also change it texturally. So with looking at sedimentary textures, we're looking at rounding and sorting. So I've got two very extremely different rocks here. When we first start breaking up our mountain, made up of an igneous or metamorphic rock, probably, could be sedimentary, that's fine, we're going to end up with big angular chunks of sediment, like this rock here called a breccia. Breccia is a sedimentary rock that's made up of very poorly sorted sediment, which means we have very different grain sizes. We've got some mud in there, we got big old chunks. It indicates a very high energy environment, generally glacial or maybe a landslide at the base of the mountains. Either way, we haven't gotten very far from the source of the rock yet. There's going to be some processes, and you're seeing this in your slides too, these concepts of rounding and sorting and how the sediment changes over time. Eventually, we're getting into a much finer grained sediment. Just imagine a river being like a big rock tumbler, okay? You have your angular chunks of rocks in your rock tumbler. They get broken down smaller and smaller, but they're also rounding. Each one is getting abraded and worn down, so the sediment is becoming more rounded, it's becoming smaller. Overall, the entire sediment is also becoming more equal as far as the grain size. So we end up with something like this claystone. Yeah, that's why we don't have very big samples of it. This was the biggest, still the biggest, but it is changing rapidly. We have these very fine grains then that are deposited. We don't have a very big range of grain sizes. They're all very, very small, leaving dust on my fingers. They're so tiny. It's all the same mineral pretty much. It's probably just clay. So there's plenty of chemical weathering going on, even as we're talking about physical, mechanical weathering and transportation. And so it's undergone extensive erosion as well. So those are two big extremes here, breccia and a claystone. It's also important to know that sedimentary rocks, why we care about sedimentary rocks, is they tell us about depositional environments on the surface of the earth. So this breccia could be very typical of deposit at the bottom of a mountain or at the edge of a glacier, or maybe at the base of a rocky, steep cliff along the ocean, like in California. The claystone